All right, so we're starting with Roman numeral 4, formed elements, and we're starting with the word hematopoiesis, which means the process of making formed elements. And formed elements are all of the sort of solid cellular components of blood, which are erythrocytes and all the leukocytes and also platelets. Okay, so let's take a look at our stem cells here. So one of the things I talk about in this lecture is the stem cells. All stem cells are not the same. Stem cells have different potentials. So when you see the word totipotent versus pluripotent versus the word multipotent in my notes, those are different levels of stem cells. So if starting with the very first one, totipotency or a totipotent cell is a cell that is able to, it means total potential, right? So this cell has the potential to become any cell in the body. It can become a neuron or an adipose cell or a muscle, or, it doesn't matter. So this total potential only lies really within the embryo. So when you're a fertilized egg, right, a zygote is dividing and creating an embryo, those cells are now, completely, they have total potential to become anything in the body. However, as tissues start to specialize, remember in the nervous system, we talked about the endoderm, the ectoderm, and the mesoderm. Now we have these cell types that are committed to only a subset of tissue types. So the word committed is used when talking about how stem cells follow a pathway, a narrower pathway into what kind of cells that they can become. So the second level down, which is called pluripotent, pluripotent means a plurality of potential. So a plural, that means many. So these stem cells are now committed to a certain lineage of cells, but they still have a stem cell property because they can become many different types of cells, but confined within that lineage. So pluripotent stem cells are the kind of stem cells that you would find in your bone marrow to make all the cells of your blood. So let's take a look at our image here. So this is a great image because it shows you everything in purple is going on in the bone marrow. From the bone marrow, the cells will enter into the bloodstream, and then from the bloodstream, a lot of these guys will enter into your connective tissues, okay, or in the connective tissues of organs. So remember how we talked about the skin within the stratum spinosum? There was a dendritic cell called a Langerhans cell, right? Well, how did that cell get there? It was made in the bone marrow, and then it traveled into the bloodstream to your skin. And then we'll talk about other organs with other immunity, like the lung and like your liver. All right, and all those cells arrive from the bloodstream. So here is your hematopoietic pluripotent stem cell, and there are two lineages you can see. There's a lymphoid lineage and there is a myeloid lineage. The lymphoid lineage is going to turn into T cells and B cells. These two cells are considered lymphocytes, okay, because they follow the lymphoid lineage of development. The natural killer cell here, the NK cell, I'm not going to talk about in this lecture, but it is related to our T cells, and so they are also considered lymphocytes. The other pathway, which is called the myeloid stem cell pathway, will create the rest of the cells, right? So we have our neutrophils, basophils, eosinophils, and monocytes. These are all of our white blood cells. Then we have platelets, and then we have erythrocytes, okay? So there are two lineages, lymphoid and myeloid. If you look at the word leukemia, just a word on leukemia. So leukemia is a cancer of white blood cells. And the white blood cells that are produced can be of both lineages. So you can actually have a lymphoid form of leukemia or a myeloid leukemia. And either way, you have an overproduction of these white blood cells. But really, it's the blast cells that are secreted into the bloodstream. So the cells that are overproduced in the red bone marrow get put out into the bloodstream at an immature stage. The immature stage is called the blast cell stage. And so you're basically flooding your bloodstream with these immature, non-functional white blood cells that are just clogging up the system and causing the energy to go to the production of the cancer cells, but not so much your platelets or your red blood cells. So these levels actually go down. So that's just one word on leukemia. Okay, it's a cancer of white blood cells, and depending on the lineage of your leukemia, you're either producing the lymphatic, the pre-lymph cells, or you're producing these other blast cells. Okay, so let's look at a couple other things before we move on. The first thing we're going to look at is erythrocytes, the red blood cells, the first formed element. And I just want to point out here, this just appeared because I just typed it in. EPO stands for erythropoietin, which is a hormone that your kidneys actually make, and they're going to stimulate the production of red blood cells. So you can see erythropoietin is important in the maturation process of red blood cells. I also want you to notice that we have this enucleation step, right? So if you look at your outline and you look at letter C, the word enucleated is there. So the nucleus is kicked out before it actually enters the bloodstream. This is to allow it to have more space for hemoglobin, which is letter D in your outline. And hemoglobin is a protein that's going to bind our oxygen and carry oxygen around. So this is a step that happens before it enters the bloodstream. And because it is enucleated, it only survives in your circulation for about 120 days. So after about 4 months, your red blood cells are destroyed, and they're destroyed in 2 organs, the liver and also the spleen. Okay, so when we talk about the liver and we talk about the spleen, this will come up again. All right, so let's take a look at the red blood cell histology slide. So this is just a slide of erythrocytes. So really they just look like little bubbles. There's no nucleus detected because there's no nucleus there. And then the little tiny dots between our red blood cells here, those are platelets. They look 2-dimensional, but they're actually 3-dimensional, right? So they have a biconcave shape. So they have a dent on both sides. This allows them to be flexible and bendable so that they can move through capillaries. Capillaries are so small that they only allow one red blood cell in at a time. So tiny, tiny blood vessels. This shape also allows more surface area for oxygen to diffuse in and out, as well as carbon dioxide to diffuse in and out. Okay, so this shape is called biconcave. All right, let's look at a rouleau. So a rouleau is a fun word, and it's a stack of red blood cells that when red blood cells travel through very small capillaries, remember I said only one fits in at a time. So these red blood cells have the ability to stack, like you have dinner plates that stack, and they form this rouleau. And so what this does is it slows down the traffic, the passage of blood within these capillaries, because if you think about it, right, your capillaries are the smallest, and they're the blood vessels, and they're the place where oxygen gases and carbon dioxide gases, as well as nutrients and waste products, need to diffuse into the bloodstream and away from the tissues. So in order for enough time for diffusion to happen, right, the blood cells need to slow down. So the oxygen inside these red blood cells have time to diffuse out into the tissues and for the carbon dioxide to diffuse in. So this is something that happens within our small capillaries, is stacking up because the blood circulation has slowed down. But this is one factor that contributes to the slowing down is the stacking of the red blood cell. But that's good because we need the blood to slow down in these tissues long enough for this diffusion to take place across the wall of our blood vessels and across the red blood cells. Okay, so we looked at letter A, B, and C. Let's look at hemoglobin. So hemoglobin is a 4-subunit protein. And each subunit, there's 2 alpha chains, as you can see. There's 2 beta chains, as you can see. And each chain is going to have a central organic molecule. This is called the heme, right? So this disc represented here is the heme. So inside the heme, there is this ball, which is represented, by the ball. It's iron. So iron, Fe positive 2, is inside. It's a necessary component of the heme molecule. Why do we need iron? Because this iron is what attracts oxygen, and it binds the oxygen so the oxygen stays inside the red blood cells, and it can allow the red blood cells, as it travels through your body, it carries the oxygen with it, okay? So if you look at your outline, each heme group contains an iron atom which binds oxygen. That's why we need it. It binds the oxygen. Let's say that, and where do you get iron, right? This is where I ask my class, where do you get iron? And you guys will say, from your diet. Because this is a metal that we can't make metals, our bodies don't do that. So we have to get it through our diet. And if you don't have enough iron in your diet, a lot of you guys already know that we have a disorder called anemia. And anemia is a condition in general. I have the general sort of definition for anemia. It's a condition where blood lacks enough healthy red blood cells or hemoglobin. So basically, your oxygen carrying capacity goes down, right? You don't have enough iron. Oxygen that you breathe in doesn't bind to anything. And so that little bit of iron that you have, will carry just a little bit of oxygen. So that kind of anemia is easy to fix, right? Just start either taking iron supplements, or you can start eating foods that are rich in iron. And then there's other causes of anemia as well. So there are other things like diseases like malaria that actually destroys your red blood cells. You can have some kind of genetic disorder, or you have problems producing hemoglobin. So any method of where you're going to disturb the oxygen carrying capacity of your red blood cells, that can cause anemia. And then I ask you guys, what are some symptoms of anemia, right? And some of you guys, if you've already suffered from anemia, or you can kind of think about, well, what does oxygen do for you, right? Oxygen is the necessary atom that allows your mitochondria to make ATP. So if you're not providing oxygen, you're not making ATP, which is the energy of your cell. So you're going to be very, very low on energy. So if you have anemia, you're going to be very tired. You might even be foggy, you can't concentrate, you can't think. Just very sluggish, and you can also, the other symptoms are that you're cold, your skin can be pale, so just things like that. But one of the most predominant signs of anemia is being tired. Okay, all right. So let's take a look at so back to hemoglobin before we leave. Just so one hemoglobin protein has 4 subunits, each subunit carrying an iron in that heme group. So each hemoglobin protein can carry 4 oxygen molecules, okay? All right, so we talked about the hematocrit earlier. It's the percentage of red blood cells. And so we're just gonna move to blood typing now. So we're gonna look at blood typing and what the RH factor is. And so we're gonna fill in this table together. But first, let's talk about the red blood cell. So on the surface of your red blood cell, we're gonna have, and this is genetically determined, right? So if you have the gene to make a protein, this is a glycoprotein. This is a protein with a sugar group on it that is A type, right? So you inherit the A type allele for the gene. You're going to make the A glycoprotein on the surface of your red blood cell. If you inherit a B, then you also make the B antigen. And so you can only have A, so you can be type A blood if you only have the A antigen on the surface. You can be type B if you only create the B antigen on the surface. You can be type AB, so we make both A and B on the surface of red blood cells. And there's another type called type O, which you do not make either. So you do not make A, nor do you make B. So you have sort of a bald red blood cell. So the Rh antigen that's sticking out here, this is a different kind of antigen that is present or not present. So you also inherit the gene for this. If you do have the Rh antigen, then you have a plus next to your blood type. If you do not have the Rh antigen, then you have a minus next to your blood type, okay? So in terms of filling in the box, let's go ahead and just use the A and B to get things started, and then we'll go ahead and add in the Rh factor. All right, so this is going to be our table that we would fill in class together, but let's do it with this program. All right, so we have our 4 different blood types here. We have type A blood. So A blood means that you only show the A antigen on the surface of your red blood cell, represented by these blue dots. antigen B, if you're type B blood, you only have B on the surface of your red blood cell, which is these little triangles. If you're type AB, you have both antigens on the surface of your red blood cell. And if you're type O, you have neither A nor B, okay? So the mantra you want to think about when you are doing problems like who can you receive blood from and what blood type can donate to what other blood type is that you never want to introduce anything foreign. Never introduce anything foreign, okay? Because you guys know that you're going to reject a foreign blood type. So remember that word antigen. We have self versus non-self antigens. So your own immune system recognizes your blood type as self, and it's okay with that blood type. But as soon as you introduce a foreign antigen, your immune system will reject that different glycoprotein because it's going to be a non-self. All right, so let's just begin with this. Who can you donate to? So if you're type A, who can you donate blood to? So you're probably thinking, all right, we can donate to our own blood type. This is true, right? Because if you give to another type A, they also have A, there's nothing to reject. Can you give it to anybody else? Yes, you can actually give it to type A, B. Okay, because if you donate to a person who is type AB, the person with AB blood has A, and the immune system recognizes that as self. So it's not going to be foreign to that person's immune system, all right? So let's go down the line, okay? Type B. If you're a type B blood, who can you donate to? Obviously, we can donate to our own blood type. And then with the same logic as used in the top one, we can also donate to type AB, right? Because a type AB already has B as a self antigen, and it's not going to recognize B as something foreign. Type AB, who can you donate your blood to? So whoever you donate it to has to be okay with A and B, and the only option out there is type AB, okay? All right, so if you're type O, that means you have no antigens on the surface of your red blood cell, so there's nothing to reject, there's nothing foreign. So you can donate to type A, type B, or type AB because your blood cell is basically a bald, antigenless red blood cell. Okay, and you can also donate to your own blood type, of course. You can donate to type O. All right, now let's look at who you can receive blood from. This is different. This is not going to be the same as who you can donate to. So if you're type A, who can you receive blood from? So obviously your own blood type we can receive from type A, but who else? Okay, you cannot receive from type AB because that B is foreign to you, right? That's a foreign antigen, your body's going to attack it. So the other option is type O, right? Type O doesn't have any antigens on the surface, and so your body will not reject anything foreign. There's nothing foreign to reject. Let's look at type B. If you're a type B, then you can receive from B, and you can also receive from O, right? Same rationale. If you're type AB, who can you receive blood from? Well, it turns out you have all the antigens, so nothing's foreign to you, right? So you're going to be able to receive blood from AB. You're going to be able to receive blood from A. You're going to be able to receive blood from type B, and you're going to receive blood from O. So all of those types are okay. If you're type O, who can you receive blood from? So because you don't have either type, you don't have type A or B, so both A and B are going to be foreign to you. So you can't receive blood from anybody with an A or a B on the surface of the red blood cell. So the only blood type available to you to receive would be type O, okay? So looking at the table here, what's blood type is going to be considered the universal donor, right? Who can donate to anybody? And that's going to be our type O. This is our universal donor, right? Donate to anybody. And this is really difficult to write with. Okay, who is our universal recipient? Who can receive blood from everybody and not have a problem with it? And that's going to be type AB. All right, so now you need to think about the RH factor. So we're going to put in pluses and minuses and think about how that works with donating and receiving. So let's just come up with a couple of different, I'm just going to pull out of my mind here. I'm just going to do an A negative, and let's go with an O positive. Okay, so those are our two blood types. So remember, the minus means that you do not have RH factor. And the O, the positive means, sorry, not the O, the positive means that you do have the RH factor, okay? So let's think about this and do our pluses and minuses. Who can you donate to? So A negative, we can donate, of course, to our same blood type, an A negative. But can we donate to an A positive? So think about that. Can an A negative person donate to an A positive? Someone who is negative does not have RH. Someone who is positive does. So if you are missing something, sure, why not? You can donate to an A positive, right? You don't have anything foreign that the A positive person is going to reject. The other option up here is AB. Can you donate to an AB negative? Yes, you can. Can you donate to an AB positive? Yes, you can. For that same reason, we can donate to an A positive, because if the receiving person has RH, but the donating person does not, right? You're not introducing anything foreign to that person that has the RH. It's nothing foreign on your red blood cell. Okay, so let's look about receiving blood from. You're A negative. Who can you receive blood from? So obviously, we're going to put in our own blood type. We can receive from A negative. Can we receive from A positive? And the answer is going to be no, because a positive blood type has RH, a negative blood type does not. And so you're introducing something foreign, aren't you? If you take an A positive person and put it into an A negative person, that positive means that there's an RH there that the negative does not have, and so they're going to reject your blood type. So A negative, and then O, we're going to receive from O negative. Can we receive from O positive? And the answer is no, for the same reason, right? We can't have any positive symbols coming into a negative, because that positive means there's a RH, which is foreign to a person who is negative for RH. All right, let's do O positive. So who can O positive donate to? Obviously, let's start with this own blood type, O positive. Can an O positive donate to an O negative? The answer is no. Okay, so again, anybody who is negative for RH does not have it. If you're introducing something foreign into that person with a positive RH, that's going to be rejectable. Okay, so that's not possible. So basically, any positive can donate to another positive. So we know that O can donate to everybody. But if you're O positive, you can donate to only the positives. Okay, AB positive and A positive. Okay. Now let's think about O positive, who can you receive from? So let's go ahead and put in our own blood type, O positive, obviously. Can we also receive from O negative? Yes, we can, because a negative does not have it. We can receive that. That's fine. There's nothing to reject. Okay. And who else can receive from? That's it. Okay. So O positive and O negative, we can't receive from A's or B's because that's going to be foreign. All right, so when you're looking at this chart, okay, hopefully that you can think about these things. So you will be asked a question on blood typing, like if you're this blood type, can you receive blood from what blood type, right? So make sure that you understand how to work this out. And if you don't, you can always come to my office hours on Zoom or email me. Okay, but this is how you would work out this material. All right, and this is just a nice, blood distribution chart. So you can see that type O blood is actually the most prevalent in all of our demographic groups. And then we have A's and B's and ABs. ABs are actually kind of on the rare side. Being positive is very prevalent, right? So most people are Rh positive. And I just want to plug right now that donating blood, if you are able to, that the Red Cross is really looking for blood donation during this coronavirus pandemic, because the buses, that go around and they go to school campuses and they recruit students to give blood, those are not happening anymore, and the blood supply is actually getting a little bit low. So if you have the time and have the ability to, you can probably seek out your closest Red Cross blood donation center and make a contribution, and you can help out during the crisis this way.